Hi friends, welcome to my channel. Let's have a look at problem 2602, minimum operations to make all array elements equal. And in this video, we're going to explain a treatment or method based on the use of partial sum and binary search. First, let's roughly look at the problem statement. So we are given an array called nums consisting of positive integers. We are also given an integer array called queries of size m. For the ith query, we would like to make all of the elements of nums equal to queries I. So we can perform the following operations on the array any number of times. So the operation is either increase or decrease an element of the array by 1. So what we are required to do is to return an array answer of size m, where the index I element in answer is the minimum number of operations to make all elements of nums equals to this query. So here is a note. After each query, the array is reset to its original state. Actually, this note greatly simplifies the problem. So this is an additional assumption. So here are two examples. Let's look at example 2 first. So the target, let's look at the query 10. So in order to get 10, so we need to increase 8 from 2, increase 1 from 9, increase 4 from 6, and increase 7 from 3. So if we add them together, so we're going to get 20. So if we look at example 1, so the 14 in the output corresponding to query 1, because 1 is no greater than odd element, so we need to decrease odd element. Let's see, this one decrease by 2, by 0, by 5, and by 7, right? So we get 14. So similarly, you can look at 5. So this 5 actually is a representative because there are elements that are less than 5, and there are elements that are larger than 5. So for the smaller ones, we need to increase to 5, and for the larger ones, we need to decrease to 5. In other words, we need to consider the distance or absolute value between the target and an element. So that's the logic here. So corresponding to 5, so we have 3 and 1 should increase to be 5. So the sum of these two are 4. So we need to use, because we have two 5s, 5 times 2 minus 4, that is 6, right? And then we have this one, so we need to decrease in each element by 5. So the total sum here is 6 plus 8, 14. So minus 2 times 5, that is 14 minus 10, right, is 4. So, right, so this gives us the 10 together. So the constraints for this problem are the following. First, m and n are the lengths of queries and nums respectively. They are bounded above by 10 to the power 5. So this number is a decent large number. So we need to pay attention when we do the coding, because if we do it in a brute force fashion, it's quite possible that it's time limited. So with that said, we are ready to explain the treatment. So here, for a given, so we can actually sort the nums. The reason is that we just need to add the absolute difference between an element and a query number for each element. But the thing here is that how we compute this effectively, right? So for a given sorted nums, so here I wrote sorted. So we have A1, A2, AN, right? So here I'm using one indexing just for convenience. It does not matter actually. So assume that we have a query number Q. So we assume that there is an index I0. So before I0 or on I0, so all the element is less than or equal to Q. So in this problem, less than or equal to or less or greater is not very crucial, because if the element equals the query number, it produces 0. right? So if I is less than or equal to I naught, we assume that odd element is smaller and otherwise larger. Then the needed number of operations is very easy to compute, right? So for the smaller ones, we need to use q minus the numbers. So we have this, this is the q, we have this number of terms, that is I naught, then minus a1 plus a2 plus a I naught, right? So this is the partial sum, actually. And then the remaining part we want to use, because it's larger than the q. So the remaining term is n minus I naught terms. So times q. So this is the thing we are going to subtract. And the sum is ai, with summation for I greater than I naught. In other words, the tail sum. So this summation actually can be reduced to the sum. First is the first term is q times I naught minus s naught, where s naught is the partial sum up to index I naught, right? So the other part is s minus I naught, right? Minus this number of multiples of query number. So this is the sum. So if you simplify, you're going to get this one, right? So you count the number of q's. This is I naught. This is negative n minus I naught. So together that is 2 times I naught minus n q. So here we have negative s naught. So here we have s minus s naught. So together we are going to have s minus 2 times s naught, right? So let's give a quick summary before we do the coding. So I naught is the insertion point, which can be easily obtained via binary search, right? So the partial sum sequence can be easily obtained. Actually, so to get the partial sum, so this is a typical dynamic programming practice. So here let's look at an uncooked example. So from example 1. So here the nums is given sorted just for convenience. We have 1, 3, 6, 8. And the query number, I pick the second one, that is 5, right? So 1 and 3 is less than 5. So we're going to have 2 times 5 minus 1 plus 3. So that is 2 times 5 minus s1. S1 is up to here, right? So that is 10 minus 4. Then 6 and 8 is greater than q. So we have 6 plus 8 minus 2 times q. That is 14 minus 10, that is 4. Together they get 10. So this is the second output in example 1. So with that said, we are ready to do the coding. So our plan is the following. First, I'm going to write our both one. So this is just for details. And then we're going to write a succinct one. So this is after the first verbose version, so that we have already understand the final details. With that said, let's first do some preparation, right? So step 0. So we do the sort. So here we can sort nums in place, right? And then we can get the length. So length nums, let's call it m, right? So query size m, right? So but it's not essential. But let's use the same notations with the problem statement. And then I'm going to produce step 1, produce the partial sums. So in this problem, I guess it's important to pay attention to the indexing, so that you do not miss terms or add more terms. So here let's have a prefix sum, so and also a suffix sum. So here I can use nums copy. Just there's lots of choices. We can do this, and then we want to first get the for I in range 1 to n. So let me first get the prefix sum. So I, the increment by I minus 1, right? So this gives us the prefix sum. Then for the suffix sum, so I'm going to iterate backwards from n minus 2 to so here we want to end at index 0. So the step is -1 and the ending point is -1, but this is not included, so we ending at 0. So we're going to have suffix s I increment by the previous one. So that here previous means I plus 1. So as we start from 1 in the first for loop, so I minus 1 is always not greater than or equal to 0. Similar here, we start from n minus 2, so I plus 1 is always less than n, right? So this way we get the prefix sum and suffix sum for us to use. Next, so we want to also consider a situation, because here the queries can be quite long, and there are some queries might be repeated. So for this, in order to reduce the number of checks, so I'm going to use a set queries, and then I'm going to use a dictionary for like a check table. So let's call it step 2. Step 2. So get distance or get a number of operations. I'm going to use distance for unique query numbers, query values. So this is actually very easy now. So first, we need to for y in this set, and then I'm going to use the bisect dictionary. So I'm going to use bisect right. So nums y. Notice that nums is already sorted, so we want to get the insertion point for this y, right? Then it means that left to this index idx or smaller than this idx, so all the element is no greater than the y, right? So the y here is a query number. So here let's make some discussion. So actually it's not absolutely necessary, but it's good to know this final detail. If idx is equal to n, which it means that all the element in the nums is less than this y. So the number of operations is given by n times the query number minus the sum. So the sum is actually, there's two ways to get. There's a suffix 0 will be the sum, or a prefix -1, the same thing, right? Otherwise, if idx equals 0, it means that all the elements in the nums is no less than this query number. Then dy will be nothing but the sum minus n times y. So the sum actually we can use prefix -1, right? So minus n times y. Otherwise, so the idx will be a middle one. Then what we are going to do is to compute the sum, depends on according to here, right? So this so here first for the left ones, I'm going to have this number of terms. So I have idx times y, then minus the prefix sum, prefix s, because idx is the insertion index. So for the sum, we're going to use idx minus 1. Because we have discussed this situation, idx is greater than 1. So this one, idx minus 1, is always no less than 0, or greater than or equal to 0, right? So this is always valid. And then we add the contribution of the sum, the tail. The tail actually is all greater than y. So how many terms? It has n minus idx terms. So this is the part we are going to subtract, right? So the tail sum actually is nothing but the total sum minus this one, right? But we can directly retrieve that because we have write this verbosely, so it's idx, right? So this is the one part for the tail operations. This is the one part for the head operations. So together they give us the operations. And then what we are going to do, we just need to check the table, right? Step 3, return. So this is actually just a list comprehension, right? So basically we want to get queries I. So this is the query value. Then we check the corresponding operations in the dictionary. Then for I in range. So queries has length m, so we here have range m. So this verbose one actually is not very long still, forms a solution format to this problem. So before we move to the second succinct version, let's first make a check. Yeah, it passes the one example. Now let's look at generic case. Yeah, it passes a generic case, but looks like it's not very fast. So now let's copy this function signature. So I'm going to mark this one as version v1, and then I'm going to add some annotation here. So this is version 1, and it's a verbose one, but for details, right? And now let's write another solution. So here, before we do this, we can make some import, if you like. So we can import from tools. We can import accumulate. So this is for computation of the prefix or partial sum of suffix sum, and then we can use from bisect import bisect left, bisect right. So actually both are okay in this problem. So this is for version v2, right? So what I'm going to do here is first let's get the length of nums. This is for convenience, and let's also maybe get the query's length. Right. So we have this one. So here again, I'm going to sort this nums in place, and then I'm going to get the accumulation sum or the partial sum. So here actually we can first I can call this accumulate. So the iterables is nums, and then the initial value for this iteration for this accumulation is 0, right? So this I'm going to transform it to a list just for convenience. Then we get the prefix sum. Then I'm going to initialize a result variable, and then I'm going to iterate over the query. So here I didn't do this one for considering multi cases, but yeah. So the idea, so if you like, you can incorporate that. So here for a query in queries. So what we are going to do is first we get the bisect. See, right? I used right as in above. So here I'm going to, this is the inserting point we want to test. And then what we are going to do, we just append the corresponding number of operations. Let's write n operations. So this is nothing but, g times q, right? So q is the query value. So before the index j, so the numbers are less than this one. So here I'm going to use accumulate g, right? In this case, and then I'm going to use the remaining sum minus the this number of terms, that is minus q, not minus g. So this is the remaining terms times q. So the tail sum actually is nothing but this total sum minus this number, right? So here again we need to pay attention to the indices. So this is the thing, and what I'm going to do is to result append this n operations for this specific queue. So after that we just need to return the results. Before we make any comments, let's first do a check. So we have changed this function signature, right? So now let's check. Yeah, it passes one example. Now let's look at generic case. Yeah, it passes all the cases. So as we mentioned here, so in the second version we wrote the first here verbosely, but we can also make some mathematical computations to write this one. Let me do this. So here I'm going to copy this this one, and then I'm going to comment out the one just for documentation. So here I'm going to simplify this. I add this one and this one together and combine these two terms. So the result is nothing but, let me write down here. So this is 2 times G minus M times Q, then plus the total sum minus 2 times the sum up to this index, right? So with that done, let's do a check, right? Yeah. So before that, we can also print out this accuracy score so that So we have one more term added, that is 0. That's why here we write accuracy or not accuracy, accumulation sum G, right? Because the first term takes a position. So, but in here we do it from directly. We are writing the index minus 1, but here is index. It's due to the difference of this adding an extra item or not. So with that said, I guess that's about it for this problem. It seems that the second version a little bit is slightly faster than the first version, but in essence they are the same thing. So with that said, I guess that's about it for this specific problem. In this video, we actually explained a solution based on the use of partial sum and binary search. So we provided two versions of solutions. The first version is more verbose. It's for the sake of understanding the details. And after the V1, so we simplify the solution and make it more shorter. So with that said, that's it for this video. So if you found this explanation useful, you can follow up my channel in YouTube. Thank you.